Okay, so we got our DNA here, which is referred as the parent DNA, which is composed of monomers called nucleotides. Each DNA nucleotides are composed of three parts. One is the phosphate group, the other one is the deoxyribose sugar, and there's 4 types of nitrogenous bases. So we can see here, guanine will always match with cytosine, and adenine will always match with thymine. These 2 pairs, or like each pair, is held together by a amount of hydrogen bonds, but the 2 pairs are different. So for example, G and C, guanine and cytosine, are held together by 3 hydrogen bonds, while A and T, adenine and thymine, are only held together by 2 hydrogen bonds. Okay, so looking more at the DNA, we can actually see the backbone, which is the phosphate and the 5-carbon sugar. Trying to figure out where to put our 5 and 3 primers, we can identify by using our 5-carbon sugar. So this is how we do it. So looking more closely, okay, I don't know if I should bring it. We count the carbons, so 1, 2, 3, 4, 5, and we try to identify the 5th one and identify the 5 carbon to the end of the parent DNA. So this is the end and this is the 5, so whatever's closest is the 5 prime end. So we can see here 1, 2, 3, 4, 5 starting at oxygen. 5 is closest to this end, so that's why we're going to put the 5 prime parent right there. And looking over here, 1, 2, 3, 4, 5. 5 furthest. Okay, what is the closest? 3. So there's only 2 types, 3 or 5, and 3 is the closest, so that's why we're going to put a 3 there. And since DNA is run anti-parallel, it's going to be the complete opposite. So if it's 5 here, it's going to be 3, 5, no, 3, it's going to be 5. We can also check that we can see here, doing the counting clockwise again. So 1, 2, 3, 4, 5. 5 is closest, so bam, bam. We get our, okay, I lost my pieces, but okay. I keep losing them, which makes me mad. Okay, so that's pretty much identifying our DNA. Okay, cool. So now we are going to start creating our daughter strands. So remember that we are gonna, where's my helicase? We're gonna start with this, our scissors called the helicase enzyme. And what the helicase enzyme is gonna do is gonna come here and cut the hydrogen bond. So cut. And I'm just gonna leave it there because it's important to know in what direction we cut our bonds. So I'm just gonna push through here and boom here. Okay, now we need to figure out where to put our daughter primes. Easy thing to do is just look at the parent primes and just do the opposite of what the parent is. So if it's 5, it's a 3. So put 3 here. And then opposite of 3 is 5. Opposite 5 here is 3. So put here. Okay. So now we need to figure out the lagging strand, and the leading strand. How do we figure those out? We have to look at the primes. So remember that we cut this way, so that means okay. Since we cut this way, we have to figure out which one is 5 to 3, because the polymerase works 5 to 3. So whatever is 5 to 3 is the leading strand. So we can see here, since we cut this way, we start here, and looking here, start at 3. No, it has to start at 5. So start 5, yes. So boom, this is the leading strand down here. Up here is the lagging strand. Now, since we cut the hydrogen bonds, the DNA is actually most chemically stable as a double helix. So it wants to, get back together, snap back. But in order to not let that happen, and ruin our whole progress, we actually have, sorry. Okay, we got these, in order for not that to happen, single-stranded binding proteins, I don't have a marker, so we just use this orange, will be attached at the backbones. Remember backbones, phosphate and the 5-carbon sugar? So it'll be attached just to make sure it doesn't snap back together. So it acts like a clip or acts like a anchor, I guess you could say. Cool. Okay, so now we got this. It's time to build. So remember how our helicase started from here? That's also where our polymerase is going to start. So let's just start with the leading strand here. I'm just going to put these away so because it interrupt. But remember, leading strand, lagging strand. I put those over here. Now, start building. And since polymerase works 5 to 3, 5 prime to 3, looking at here, this is a 3 prime, so it's not going to start here. It's going to start here. And it starts building. So the polymerase is going to come in the direction of what the helicase came into. So going this side. So first, remember starting with the leading strand, we see polymerase sees that, oh, it's a C. So what matches, what will go with the C? A G, which is guanine. So we're going to take, the polymerase is going to C. So it's G, okay. Next one could be T. So bada beam, it sees that it's guanine, so it's going to attach a cytosine. It sees a adenine, so it's going to attach a thymine, and then so on, so on. So I'm just going to put G for C, C for G, T for A, C for G, and then A for C, and then what else? I need a, what is it called? Okay. Okay, where is it? Okay, boom. Bada bing, bada boom. Okay, so after that's done, so polymerase. Now there's actually a different enzyme of polymerase, a different polymerase that comes in and I guess double checks to see if there's any errors, right? So it spots, and then looking at it, okay, it's good. G, good, 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 good. It's checking, you know, the pairs that they're actually well matched. So good. Oh, we see C and A. Remember, A always goes to T. So take this out and replace it with a correct one, which would be a T, thymine. And boom, that's how we got our leading strand. Next one, the lagging, building the lagging strand. So polymerase wouldn't be able to start building right away. Why? Because 5 to 3, remember, it only builds 5 to 3, but unfortunately, on the way of how we cut the hydrogen bonds with the helicase enzyme, we started from here, and what starts here? 3. So we can't start. But there's only one way that polymerase would actually start building if it actually spots something called the RNA primer, which will represent at this with this little thing. So the DNA primates actually drop these RNA primers, which is like a little clump of nucleotides that's covered by RNA. Now, you know, at random, or there's a reason, but let's just say put this here and then put this one here. So then start building, right? So the polymerase won't start until it sees the RNA primers. So the polymerase spots one, so it starts building to the right, 5 to 3. So starting here with the polymerase. So we'll get a T, and then we'll get a C, and a T, and then a G. and then boom, and it won't build until it sees another one. There it is. So it's an A goes with the T, remembering the complementary pairs, and boom. And you see there's little gaps that happens between the Okazaki fragments. These little chunks are called Okazaki fragments. And then boom, the last one, Polymerase sees it, scan, and boop, so it starts building. Okay, almost done here. So when it's, let's just say we're done here. Oh, wrong one. Done here, we can see that there's little gaps. So one of the last steps is a different kind of polymerase comes and removes the RNA primers. So removes, and removes. And then ligase would come along, and ligase would come and pretty much glue, or we'll look for breaks, these little spaces between the Okazaki fragments, and we'll pretty much glue them together, and goes like that. And there you go, pretty much. So the next step we do is actually remember these SSB, single-stranded binding proteins. So we just remove this, remove from the backbone. And then once we do that, it kind of allows each DNA strand to spiral into a double helix. And yeah, mitosis happens. That's mitosis. And boom, 2 strands of DNA. So yeah.